So this video is going to take you through Unit 2.5 Organic Chemistry, the bits and pieces that were missing from the other two videos which were based on the old specification. So I'm just going to take you quickly through those now, starting on page 4. So the study of organic chemistry is really important because organic compounds make up a large amount of the materials and the compounds that we use every day, right from the desks that you're probably writing on now, to the sugars that you'll eat in a lot of the foods you eat now, and even us as humans, we're made up of organic compounds as well. Here you've got a list of lots of different organic compounds: plastic cups, wooden desks, sugar, paints, medicines, clothes, cosmetics, fuel, and even us as humans. So all of these things are made up of organic compounds. So you can see the study of organic chemistry is very important because it affects our everyday life. So what is it that links all organic materials together? What is this study of organic chemistry about? Well, you may have heard this in the first video in the introduction, that organic chemistry is all about the element carbon. So all organic compounds contain the element carbon. And there may be other elements there as well, but it must contain the element carbon. And we've seen just from that list above, that minor list above, and there's so many more, that organic materials are used in all areas of our lives. So it's really important that we study organic chemistry, and it makes up a large part of the chemistry industry. And it's estimated that over 300,000 new carbon compounds are discovered each year. That is a lot of new compounds every year. So why is it that carbon can form so many compounds? Well, you'll have seen a little bit of this if you have watched the Alkenes video. But first of all, a carbon atom can form a single bond or a double bond to other carbon atoms, and that can make chains and rings of different lengths of carbon atoms. So for example, if you've watched the video on alkanes, you'll have seen that the first alkane is methane, and it has one carbon in its chain. Then the next alkane in the series is ethane, and ethane has 2 carbons in the chain, and this can go on and on and on. We can have an alkane with 3 carbons, 4 carbons, 5 carbons, 6 carbons, and already as you build on the chain length, you're forming new compounds. So carbon can form many compounds because it can form these chains of different lengths. It can also form double bonds to each carbon atom. So for example, if we look at ethane, if we put a double bond between our carbons instead of a single bond, there would actually only be room for 2 hydrogens on each carbon atom. And that's a molecule that we call ething, not ethane. And we'll come on to that as the next section of the topic, looking at alkenes, and that's a totally different family of organic compounds again. So you can see that even just by changing the bonding within a compound, you've created a whole new family of compounds. So there's lots and lots of carbon containing compounds. Another reason why it can form so many compounds, not only can it bond to other carbon atoms with double or single bonds, but it can also bond to other atoms such as hydrogen, which we've seen in our alkanes, but also oxygen and chlorine. So if I was to change with methane one of these hydrogen atoms for chlorine, there you've got something called chloromethane, which is another carbon containing compound. So it can form many compounds because it can form carbon chains of different lengths and carbon rings of different lengths, but also can bond to other atoms, for example hydrogen, oxygen and chlorine, amongst many others. So over on page 5, we are looking at bonding in organic compounds, and you may have heard this in the second video that you went through, and you may have filled this in already, in which case you can skip past this part, but just in case you didn't go through that because it wasn't in the same order in your notes, just to take a brief look at the electronic structure of carbon and its bonding and why it forms the number of bonds that it does. So up at the top of this page, I've got a section of the periodic table, just kind of the top half of the periodic table, and looking at carbon and where it sits in the periodic table. It's here. Okay, so you can see that its symbol is C, its atomic number is 6, and its mass number is 12. So looking at the electronic structure of carbon, well, I can tell from the atomic number that it has 6 electrons. So let's draw that in now. So if we draw carbon, and then our first shell will contain 2 electrons. And then the second shell will contain 4, because we must have a total of 6 electrons. 2 go in the first shell and 4 go in the second shell in separate positions at north, east, south and west. And this is why it's really important that we order our electrons the way that we do. And because it tells us something about the bonding. And what we know from our study of bonding in year 11 is that it is the electrons that are on their own that get involved in bonding. So electrons that are in pairs tend to stay that way and tend not to separate. But the ones that are on their own, they want another electron to pair up with so that there's a full outer shell. So at the minute, carbon has 4 electrons in its outer shell, and so essentially it needs to gain another 4. To get a full outer shell. Now it doesn't gain electrons as such, it tends to share electrons with other carbon atoms to give it a full outer shell. So essentially bonding can happen at these 4 positions. Bonding can happen at these 4 positions. So if you think about, on the previous page we were talking about methane, and I drew it like this: carbon bonded to 4 hydrogen atoms. So why is that? Well, those hydrogens are essentially coming in at the 4 points, the 4 electrons that we have got drawn here already. If you see hydrogen up at the top of the page here, its symbol is H and it has just 1 electron. So if we were to draw that in, it would have just 1 electron in its outer shell. So essentially when carbon is bonding with hydrogen in methane, it comes in like this and it shares its electron with carbon. And we have 1 hydrogen at each of these positions. So that's just one example with methane, how other atoms would come in and share their electrons with carbon. Carbon atoms can also do this with other carbon atoms, because each of these carbon atoms is going to have 4 single electrons that can form bonds with other atoms, and they do that by sharing electrons. So it's all about covalent bonding here. Thinking back to year 11 bonding, the sharing of electrons is covalent bonding. So where we have 1 shared pair of electrons is 1 single covalent bond. So you can see that with carbon here. So you don't need to draw in any of your hydrogens there as such. What we want there is simply just what we have here, the electronic structure of carbon. So if you have drawn in that example of methane, it might be worth just drawing that simplified electronic structure of carbon. That's all we want in this gap. So essentially what we want to write is that there's 4 single electrons that are available for bonding. Okay, so 4 electrons in its outer shell. 4 electrons in carbon's outer shell available for bonding. And what that actually means is that carbon can form a total of 4 bonds. So it can form 4 bonds. Now you don't need to be able to explain that from its electronic structure, but it's helpful to see how carbon must have 4 bonds to complete its full outer shell. So just filling in this box down below, we'll move that all up here. Carbon is in group 4, you can see that from the periodic table, and that means its valency is 4, and essentially that means that it needs to form 4 bonds to get that full outer shell. So when you are, and we will be doing this a lot later on in the topic, and you may already have done so if you've watched the Alkenes video, you must ensure that all carbon containing compounds, that in these organic compounds your carbon has 4 bonds in total. Otherwise it doesn't have a complete outer shell. So you must check that when you're drawing organic compounds that the carbon has 4 bonds. So we've seen that carbon has 4 electrons in its outer shell, and we've seen that that means it forms 4 covalent bonds. 4 covalent bonds in all of its compounds. And we've seen that in how it shares electrons rather than gaining electrons or losing electrons. It shares electrons to get that full outer shell and form those 4 covalent bonds, just as I showed you with methane. And those 4 bonds can be single bonds or double bonds or a mixture of double and single bonds. So let me just show you, for example, ethane. So I'll draw this in the box here. So ethane would be carbon connected to one other carbon, and remember then it must have 4 bonds. So we'll draw the additional bonds in for each of the carbon atoms and put hydrogen at the end of each of those. So you can see that because I've just used single dashes, that means that's representing single bonds, and this molecule is called ethane. It's an alkane that contains 2 carbons. I'm then going to show you ething. So ething is where instead of a single bond between the 2 carbon atoms, you have a double bond. So that double dash is representing a double bond. Again, remember each carbon atom has to have 4 bonds. So you can see this carbon on the left, if I start with it first of all, it has 2 bonds currently to the other carbon atom, so it needs 2 more. And that's where our hydrogen atoms go. And then the carbon on the right, again, it has 2 bonds currently and it needs 2 more. 1 to each hydrogen atom. So here you can see there's a mixture of double and single bonds. There's a double bond between our carbon atoms, but there's single bonds between the carbon and the hydrogen atoms. This is called ething because of that double bond between the 2 carbon atoms, which I'll go over in red here. That's ething, and it's a molecule called an alkene. So from this page, really what you want to take away is that essentially carbon has 4 electrons in its outer shell, so it forms 4 covalent bonds in all of its organic compounds, and that can be single bonds, which count for 1 bond obviously, or double bonds, which count for 2. Single electron. On page 6, the only thing I really want to take you through is the definition of hydrocarbons. The rest of that is there in your notes. It's complete in your notes and was in the videos. I'm just aware that the audio cut out when I was explaining hydrocarbons in one of the videos. So just to explain, you are quite often asked a definition of what a hydrocarbon is, and you have to be very careful about your definition of it, but you can essentially tell it from the name. So the name is hydrocarbons, so you've got hydro, and then you've got carbons. The hydro part refers to hydrogen, and the carbons part refers to carbon. So essentially a hydrocarbon is any substance composed of hydrogen and carbon, but there's another word in your definition that you must include. So it is composed of hydrogen and carbon only. So put that in red and make that stand out. Hydrogen and carbon only, and that's really, really important. So hydrocarbons only contain hydrogen atoms and carbon atoms. They don't contain anything else. So let me show you an example of this. So for example, we could have ethane. I've just showed you that molecule. So you've got 2 carbon atoms, and then you have got 6 hydrogen atoms in total, 3 on each carbon atom. So that's ethane. It is a hydrocarbon because it contains hydrogen and carbon only. There's no other atoms there. But let's say, for example, I now show you chloroethane, which is where we substitute one of the hydrogens for a chlorine atom. So we'll fill up with 5 hydrogens, and then what I want to do is put a chlorine here at the end. So you can see I've just changed ethane by 1 atom. I've changed 1 hydrogen for 1 chlorine, but this is no longer a hydrocarbon because our definition of a hydrocarbon says that a hydrocarbon is any substance composed of hydrogen and carbon only. Because we now have a chlorine, therefore it does not fit the definition, because it contains carbon, hydrogen and chlorine. So you just got to be really careful to include that word only. So you can see that chloroethane, as we would call it, contains hydrogen and carbon, but because it contains chlorine as well, it's not a hydrocarbon. The rest of this page was covered in the other videos. Over to page 7, and again most of this was covered in the videos, but just to make sure that you've got this gap filled in. So this is talking about the fractional distillation of crude oil, and you've got your definition there. Fractional distillation is the separation of a mixture of liquids based on their boiling points by boiling and condensing and collecting simpler mixtures called, and you should know by now, but these are called fractions. So the different simpler mixtures that are separated out are called fractions. So think fractional distillation, what comes out of those is what we called fractions. We've talked about in great detail in the other videos about the boiling point of the hydrocarbon being related to its length, or essentially its size, and the longer the chain of the carbon atoms, the higher the boiling point. So you would have seen that the longer hydrocarbon chains come out at the bottom of the fractionating column where it is hotter. So I'm not going to go over all that again, but included in your notes is a helpful summary of fractional distillation. Quite often this is a 2 or 3 mark question where you're asked to explain the process of fractional distillation of crude oil. So here's the key points here. So number 1, the crude oil is heated to over 400 degrees C and vaporised. Again, you don't necessarily need to quote that temperature as such, but if you wrote the crude oil is heated and vaporised, so I'll put that in brackets. You don't necessarily need to quote that temperature, but the key points there is the crude oil is heated and vaporised. Point number 2 is then that after it is heated, it is passed into the fractionating column, and it's really important to say that at this stage it's crude oil vapour, so it's a gas at this stage. So the key point with 1 and 2 there is that you're heating the crude oil before you put it into the fractionating column. So it's not actually being heated in the fractionating column, in which case heat would rise, but it's actually being heated first and then passing into the fractionating column, where actually it's cooling as it passes up the fractionating column, which again you'll be familiar with from your previous videos. But again, if you were asked this in exam, you wouldn't need to say the crude oil vapour is passed into the fractionating column, which is hotter at the bottom and cooler at the top. If you just wrote what I highlighted there, that's the key point. The crude oil vapour is passed into the fractionating column. That's the second key point. And the third key point then is in the fractionating column, the hydrocarbon fractions separate based on their boiling points. And again, if you were simply describing the process, that's all you'd need to write. But it just goes on a bit and explains that the hydrocarbons cool as they rise up the column and condense at different heights at their different boiling points. It's essentially just explaining it. So your key points there are the crude oil is heated and vaporised. The crude oil vapour is then passed into the fractionating column, and in the fractionating column, the hydrocarbon fractions separate based on their boiling points. So make sure you know those 3 key points really well, and I've asked you in your assignment to include those on your summary sheet, on your revision sheet, to make sure you know that really well. So over on page 8, again, I don't want to talk about this in much detail because you looked at this in the other videos, but just looking at what is missing in your notes. So again, you've got that step number 1 where the crude oil is heated and vaporised. Okay, and that's at roughly 400 degrees C. Okay, and then it passes into the fractionating column, crude oil in as a gas. That's number 2. It's passing into the fractionating column as a gas, and then this essentially here is step number 3. That when it passes into the fractionating column, your different fractions, your simpler mixtures, are separating out based on their boiling point. So as we know, we're not actually heating it in the fractionating column, so it's actually cooling as it rises. So it's hot at the bottom and it's actually cool at the top, which seems counterintuitive, but it's the fact that it's passing in hot and we're not actually supplying any more heat to it in the fractionating column. So that means that your fractions with the higher boiling points will condense first of all, and therefore the fractions at the bottom will have the higher boiling points. Because what we mean by that is, say for example they had a boiling point of 350 degrees C. That means if we were heating it up, it would boil at 350 degrees, it would change into a gas at that temperature. But if we were cooling it back down, once it gets to 350 degrees C, it's going to turn back into a liquid and it's going to then separate off. So those are your higher boiling points, and these are your longer hydrocarbon chains. So remember we talked about in the previous page that the boiling point is directly linked to the length of the chain, or essentially the size of the molecule, because it will have a higher boiling point. The larger the molecule is, the higher the boiling point it will have. So it's your longer hydrocarbon chains with the higher boiling points that are separating out at the bottom, and it's your shorter hydrocarbon chains with the lower boiling points that actually make it all the way to the top as a gas, and then eventually when they reach their boiling point, or in other words the point at which they condense back to a liquid if they are cooling down, then they will separate out off at the top. So this is your lower boiling point at the top, and those are from your shorter hydrocarbon chains. So essentially the length of the hydrocarbon chain is getting shorter as you rise up the fractionating column. Your shorter hydrocarbon chains are at the top of your fractionating column because they have the lower boiling point, so they will rise up further as a gas. They will stay as a gas longer essentially until it's cooler and reaches the point at which it turns into a liquid again. And it's your longer hydrocarbon chains that have higher boiling points, so it will separate off down at the bottom of the fractionating column where it is hotter. So just to summarise that here in this in these 2 bullet points, large hydrocarbon molecules are collected near the bottom of the column since they have a high boiling point. And the small hydrocarbon molecules are collected near the top of the fractionating column since they, and that should be have, not give, since they have a low boiling point. So just make sure that's filled in so that it's summarised there on your page. If you flick over to page 9, then it was covered in the other videos, so we're going to go straight to page 10. So this is over on page 10 now, and we're going to talk about the process of thermal cracking. So essentially the summary of this is that short chain hydrocarbons, short chain alkanes, are useful as fuels because they burn very easily and they release a lot of energy when they burn. But the longer chain alkanes are less flammable, and so they're not in so much demand. So we know in our fractionating column we collect different fractions. We've got our shorter chain alkanes up at the top, which are useful. But then you've got your longer chain alkanes as well, and we don't want to waste them as such. So this is a process that we can use to essentially break up the longer chain hydrocarbons into shorter chain hydrocarbons, and therefore they are more useful. So essentially we're just breaking up the chain. So if you think of just breaking a chain in the middle essentially, and this process is called thermal cracking. So cracking, essentially you're cracking the chain. And thermal means that you're using heat. So here's your definition here, that the thermal cracking is the breakdown of longer or larger saturated hydrocarbons, alkanes, into smaller, more useful ones, some of which are unsaturated. And we'll talk about that in a wee second when we look at an example. And the alkenes that we produce as well, they can be used as starting materials to make other substances such as polymers, which are quite often used to make useful materials like plastics. So cracking can be carried out by heating, and therefore we call it a thermal decomposition. Since we're not reacting these longer chain hydrocarbons with anything else, they're not undergoing a reaction with something else, but they're essentially just being heated, and they're breaking down into smaller molecules, and multiple smaller molecules. So we're going to have a look at an example here of decane. So decane is an alkane that contains 10. So dec means 10, and we can tell from the ANE part that it's an alkane. So it's an alkane with 10 carbons. So I'd like you to try and draw that for me, please. So you could even pause the video, try and draw decane, which has a total of 10 carbons in the chain. So hopefully you've given that a go, but if not, draw where your starting point is drawing a long chain that has 10 carbons in it. And then what I want you to do is think about how many bonds does each carbon need, and fill those up with hydrogens. So give that a go now. Pause the video, see if you can complete your molecule of decane. So there's what your decane molecule should look like overall. So the two end carbons will need to have 3 hydrogens, and then all the carbons in the middle of the chain will need to have 2. Again, you're checking that each carbon has a total of 4 bonds. So let's think what the formula of this is. Well, we know we've got 10 carbons, so it's going to be C10. With your hydrogens, you can count them all up. You can see that you have 10 at the top, 10 at the bottom, and 1 each side. Or you can follow your general formula, which, remember, for alkanes is CnH2n plus 2. So if n is 10, then 2n is going to be 20, plus your 2 is 22. And you can count your hydrogens up to check that you have a total of 22 hydrogens. But if you have 10 along the top row, 10 along the bottom, and then 1 each side, and 1 to the left, 1 to the right, that's 22. Okay, so if we take decane as itself is not very flammable. It's one of our longer chain hydrocarbons. So we're going to break it down into a shorter molecule, and we're going to break it down into octane. So have a think. What do you think? How many carbons do you think octane has? O-C-T-A-N-E. Oct means 8, so there's going to be 8 carbons in the chain. Do you want to try and draw that now? So pause the video and try and draw octane. So there's octane. I've drawn it now. You can check that your octane has 8 carbons. Okay, so it's 8 carbons, and make sure every carbon has 4 bonds, and you fill those up with hydrogens. So let's think of its formula. It is C8H18. Okay, again that follows the general formula. If n is 8, then 2n is 16 plus 2 is 18. But you can check your diagram has those. But we've obviously broken off a hydrocarbon chain off that as well. So that is octane, but we've formed another hydrocarbon chain as well. But let's think about how many carbons and hydrogens we've got left. So if we had 10 carbons and octane has 8, then we're left with 2 carbons. With hydrogens, we had 22 in decane. We have 18 in octane, so that means we're left with 4 hydrogens. So let's try and draw that molecule now. So we have carbon, and then we only have 4 hydrogens. So let's draw them like this. 1, 2, 3, 4. 2 on each carbon. But you can see there's a problem here. Each of our carbon atoms only has 3 bonds rather than 4. How we solve that problem is we put a double bond between our carbons. We talked about that earlier in this video, that carbon can form a mixture of double and single bonds. This is what we call an alkene, which we will come on to in the next section. But we can't just add 2 more hydrogens because there are no more hydrogens in decane, so we can't just form 2 hydrogens out of nowhere. So this molecule has the formula C2H4. And it's what we call ething. So I'll write all of the names underneath. Let's just move this up slightly. So this is ething. This is octane, or C8H18. And this was decane. So this is decane undergoing thermal cracking to form octane and ething. So why did we do this process? Well, what we said was these longer chain alkanes are not as useful. So this is longer chain alkane. And it's not as useful. Why was that again? Because it's not as flammable. It doesn't burn as easily. So if we want to use these alkanes for fuels, we need shorter chain alkanes that are more flammable and can be more easily used as fuels. So what we formed is octane, which is a shorter alkane. It's only 2 carbons shorter, but already it is more useful. It is used as fuels because it's more flammable, and that's summarised at the top of the page. And we also form an alkene called ethene. And as we said earlier on, they're quite often used to form polymers such as plastics. Okay, so they're used to make polymers. So for example, ething, the polymer of ething would be polythene, which is used as a plastic. Okay, so from this thermal cracking, what we've done is we've taken a longer chain hydrocarbon, which is not that useful because it's not very flammable, and we've formed two useful products out of it. A shorter chain alkane, which is used as a fuel, and an alkene, which can be used to make polymers, which many useful substances can be made out of. The next few pages are covered in the previous video, so we're going to skip now to page 15. So if you could skip to page 15 with me now. So you'll already have had an introduction to this when you looked at naming alkenes in the second video, but this is just, I added this in the notes to essentially summarise how you name organic compounds and how you base that on the length of the carbon chain. So in organic chemistry, compounds are named according to how many carbon atoms it contains, and then the ending of the name refers to the homologous series that it belongs to. Okay, so you'll have met this part in the alkanes video, but the little prefix, the start of the name, corresponds to the length of the carbon chain. So that's how we start off our name. And one carbon atom has the prefix meth. Two carbon atoms has the prefix eth. Three carbon atoms has the prefix prop. And four carbon atoms has the prefix but, B-U-T. So those you do need to learn, okay, you need to learn the order of those. After that it makes sense. You don't need to know these, but after it makes sense. So for example, pent is 5, hex is 6, and so on. The likes of oct is 8, and think of the shapes that refer to or that link with those prefixes. So pentagon has 5 sides, hexagon has 6 sides, octagon has 8 sides. So after the first 4 they kind of make sense. So you need to learn those first 4 really well, and I've got a couple of common rhymes to help you remember that. First of all is the one I learnt at school, which is my elephant's poo is brown. So methane, ethane, propane, butane, for example, if we were referring to alkanes. Or monkeys eat peanut butter, and that's referring to your first 4 prefixes. And then the ending of the name depends on the homologous series that it belongs to. So if it's an alkane, it ends in ane. So you get your prefix based on how many carbons there is, and then you would put ane at the end. If it's an alkane, it's going to end in ene. If it ends in, or if it's an alcohol, it will end in anol. And if it's a carboxylic acid, it will end in anoic acid. So if we have an alkane with 2 carbon atoms, what would it be called? So the fact that it's an alkane determines the ending of the name. So the ending will be, and look just above, the ending will be ane. 2 carbon atoms, we need to go back up to our prefixes. 2 carbon atoms, the prefix, the start of the name is going to be eth, E-T-H. So essentially the name is ETH, meaning it has 2 carbon atoms, and then ane, meaning that it's an alkane. So the number of carbon atoms determines the start of your name. The homologous series, the family it belongs to, determines the ending of the name. Let's do one more with you, and then I'd like you to try the others. So 1 carbon atom, that's essentially where we start. That means the prefix is going to be meth or meth. And then it's an alcohol, so that means its ending is anol. So we put those together and we get that this organic compound is called methanol. I'd like you to pause the video and try the next 2, and then I'll go over the answers. So pause the video now and try those next 2. So So the next one is an alkene with 4 carbon atoms. So the 4 carbon atoms means that the prefix is going to be bute. And an alkene means that I end in ene. So it's butene. And then a carboxylic acid with 3 carbon atoms. Well, 3 carbon atoms means the prefix is prop, P-R-O-P. And then it's a carboxylic acid, and so it ends in anoic acid. So the anoic goes with the prop, and then it's a new word for acid. So propanoic acid. So there's a general way of learning how you name compounds. So if you were asked in an exam to do it this way, this is very, very easy marks. Your number of carbon atoms determines the start of the name. Your family that it belongs to determines the end of the name. Again, the next section is all in your notes, and we're going to flick forward now to page 22. So if you could turn to page 22 with me. So looking now at page 22, is you've covered all the alkenes, the structure of them and so on in the previous videos, but just part of page 22 was not in those videos. So what we're looking at the minute is looking at writing equations for the combustion of alkenes. And the previous videos will have taken you through worked example 1 and worked example 2, but you should have noticed that there's a third worked example in your notes, and that's the complete combustion of propane. So hopefully you gave that a go yourself, and if not, I would like you to give that a go now. I'm going to run over the process of it first of all, and then I'd like you to give it a go. So worked example 2 should be complete from the videos, but worked example 3 will have a go at now. So what you need to do first of all is determine your formula of propane. Will be the easiest way to start. So what does prop mean? Prop means that there are 3 carbons. Your general formula for alkanes is CnH2n plus 2, or you can draw out propane, either way is fine. But following that general formula, if n is equal to 3, then 2n is going to be 2 times 3, which is 6, plus your 2 is 8. So the formula of propane is C3H8. Again, you could get that very quickly by drawing out a carbon chain, where you have 3 carbons, and then count up how many hydrogens you would need to make 4 bonds per carbon. So you would need 3 for this carbon, 2 for the middle carbon, and 3 for the end carbon. If you count up, you don't even need to write your hydrogens. You would need 1, 2, 3, 4, 5, 6, 7, 8 hydrogens to fill those bonds. So the formula of propane is C3H8. So that's the first thing you need to do. Then in terms of writing your balance symbol equation for the combustion of propane, you need to choose your correct product. So remember, complete combustion gives you carbon dioxide and water. Incomplete combustion gives you carbon monoxide and water. This is the complete combustion of propane, so think about what your products are going to be. The second step is then to balance your carbons with carbon dioxide. Step 3 is to balance the hydrogens with water, and step 4 is to balance the oxygens with O2. So I'd like you to pause the video now and have a go at that yourself if you haven't already done so. If you have, you can kind of flick ahead and see if you've got the right answer. So pause the video now and give that a go. Okay, so let's go through this now. So first of all, you have to choose the correct products. So because it is complete combustion, your products are going to be CO2 and water. So let's try to start writing our equation now. So we know that we're burning propane, we're combusting propane. So we said the formula of propane is C3H8. Combustion reactions are propane reacting with oxygen, so we write plus O2. Then we write our arrow. What are our products? They're carbon dioxide and water, CO2 plus H2O. The next step is that we need to balance the carbons with CO2. So if you've got to this stage, maybe try and pause the video and try to balance it yourself. if you haven't already done so. If you maybe needed help with the first step, pause the video now and try and balance it. Balance the carbons first, then the hydrogens, then your oxygens. Okay, so let's have a look at this now, and you'll see I have changed step 2, 3 and 4 to a different colour, and that's just because I'm going to balance it up at step 1 just to save me writing it out each time. So the first thing I need to do is balance my carbons with CO2. So you can see on the left I have 3 carbons, and so that means I need to put a 3 in front of my CO2 to give me a total of 3 carbons. So that's the first step, put a 3 in front of your CO2. The next step is that we need to balance our hydrogens with water. So you can see on the left hand side that I have 8 hydrogens. But what I need to be careful about is with my waters, remember that any number I put in front of water is going to give me twice as many hydrogen. So you might jump in there and put an 8 in front of your H2O, but over at the side I'll show you why that's wrong. If I put 8 H2O, how many hydrogens would I have? I would have 8 times 2, which is 16 hydrogens. So I can't just put the same number. So whatever number I'm putting in front of my water, it's going to double. So I need to put a 4 in front of the water. So essentially you half the number of hydrogens that you have on the left and put that number in front of water. So I have 8 hydrogens on the left, so I need to divide that by 2, and that gives me 4 waters. Now this next step is probably the most tricky one, but you just got to be careful with it. So the next stage is to balance the oxygens with O2. So in order to do that, first of all, I need to count up how many oxygens I have on the right hand side now with my new balancing numbers. So you can see within carbon dioxide, I have 3 times by 2, which is 6 oxygens. Within my water, I have 4 multiplied by 1 this time, which is 4 oxygens. The plus sign in between these formulas means I need to add up my number of hydrogen or my oxygens. So I have 6 plus 4, which is 10 oxygens in total. So I need to balance that with the oxygens on the left hand side, the O2 on the left hand side. But again, any number I put in front of that formula is going to multiply the number of oxygens by 2 because it's O2. So again, I need to do, okay, I have 10 oxygens on the right, divide that by 2, gives me 5 O2 molecules. Again, you can check that because you've got 5 times by 2, which is a total of 10 oxygens. Again, you can make your list and balance that, but if you followed that process carefully, that should be your final balance symbol equation. So your final balance symbol equation is C3H8 plus 5O2 reacting to give you 3CO2 plus 4H2O. And again, get a little bit of extra practice with that. So you've got 4 alkanes that you need to know: methane, ethane, propane and butane. So methane has 1 carbon, ethane has 2 carbons, propane has 3 carbons, butane has 4 carbons in the chain. And you could be asked to write the equation for the complete or the incomplete combustion of any of these, and they could ask you other ones as well, like octane or decane, the complete combustion of them, but they would give you the formula of that alkane. But for methane, ethane, propane and butane, you would be expected to know the formula of that and be able to write a balance symbol equation for the complete or incomplete combustion of either. So what you could do is take a spare page now and do a little bit of extra practice of that. So write the equation for the incomplete combustion of ethane, then the complete combustion of butane, then the incomplete combustion of methane. Mix it up a little bit and make sure that you get those correctly. Complete and incomplete, just remember the differences in your products. Complete combustion, you get carbon dioxide and water. Incomplete combustion, you get carbon monoxide and water. So give yourself a little bit of extra practice with that process as well. And that should be everything that is missing from your notes from the other 2 videos. So that now completes the first few sections of this topic: your introduction, fractional distillation of crude oil and alkenes. And the next video will move on with alkenes.